All right. So let's start with this example or question. It's similar to what we did yesterday at the end of the class. You have a bar with 200 newtons of weight, and you have a 700 Newton person. So this person is of 700 newtons of weight, 1 meter from the hinge or pivot, and you have a rope. So you have two questions here. The first one is asking you, when the person is 1 meter from the support, what is the tension on the rope? Okay, so what you have to do first is you want to draw the tension like that. You have the weight of the bar, which is 6 meters long. And you have the weight of the person like this. That's 700. So you have two forces going down, and you have the tension acting at this point on the extreme. So you know that for both questions, you need the second condition of equilibrium, which tells you that the sum of torques respect to the hinge or pivot is equal to 0 newtons. Okay, that's the second condition of equilibrium for that to actually happen. So this tension is not perpendicular, but we can find the perpendicular component of the tension by doing the tension there. That's tension, the angle is 60, so that's sine 60. We use the perpendicular component because the parallel component won't give any torque. Okay, so we only need this. So direction-wise, we have that this force is pulling it upwards, while these two forces are pulling the bar downwards. So the torque going up is equal to the torque going down. Okay? So the torque going up is only due to this force, T sine 60, right? Remember that torque here, torque magnitude-wise is RF sine theta. But for these free cases, for the free forces, the angle is 90 degrees, so sine of 90 is 1. The torque going up is T sine 60 times 6. That times 6. The torque going down is the torque due to the mass of the bar, which you should know by now, the weight of the bar acts at the middle. So if this is 6, then the 200 acts 3 meters from the support. 3 meters. So here you write 200 times 3 plus 700 times 1. Like that. Okay? So you have T sine 60 times 6 equals to 600 plus 700, 1300. So your tension will be 1300 over 6 sine of 60. Be careful, make sure your calculator is in degrees. All right. Otherwise, you can make a mistake. All right. So then the answer for this is 249 newtons, 250 probably newtons. Okay. So that's how you solve for the tension. Similar to what we did yesterday, but now we added another mass, another weight here. So this torques, okay? The torque on one direction is equal to the net torque on one direction is equal to the net torque on the other direction. Okay, so that's part A. Part B, when the tension is 900 newtons, so if T is 900, what will be the value of X? So part B is asking you how far can the person move along the bar, on the bar, for the tension to be 900 newtons. So it's the same setup. The only difference is that now you don't know the value of X, so you don't, it's not 1, it's X. And you know T, it's 900. Okay, so this is part A. But now for part B, right, is the same. Now this is just X. And this is 900 newtons. So that still works. T sine 60. So the torque going up is T sine 60, 900 sine 60 multiplied by 6. And the torque going down is 200 times 3, that doesn't change. So that's 600 plus 700x. 700 times x. That's what you want to find. So linear equation, right? 900 sine 60 times 6. 900 times sine 60 times 6. That is 4698 equals to 600 plus 700x. So if I do this minus this, is 4098 equals to 700x divided by 700. It should be around 5. Let's see. 5.85. Ah, okay. So the person can move all the way to here for the tension to be 900. And it makes sense because the tension on part A was 250. So 900 is like the limit, right? It's like the upper limit before it probably like falls. All right, so that's another problem on torque. I'll do another one. All right, that's another example. An application of torque, which you guys have in the assignment, is your arm, right? And what's the point of rotation of your arm will be your elbow. So I will do a problem like that. There is one in the same gauge. There's quite a few actually, but there is one really interesting. Okay, we can do that at the end as a review. But now that we know torque, and now that we know that there is the second condition of equilibrium, what if a body is free to move? due to a torque, like when you open or close a door. So let's recall the concept of torque. If the angle is 90 degrees, right? If sine of 90 is 1, then we have this equation. Magnitude-wise, torque equal to RF, right? Now, by Newton's second law, force equals to mass times acceleration. So I can substitute this here. And that's what I do. Now, remember, R mass, this acceleration is the tangential acceleration, because you basically have this situation. You have like a wheel, and you have a force acting tangential to the wheel, and you are pulling it, and you are producing the rotation, which is basically what gives you your torque. So we know that the tangential or linear acceleration is equal to alpha r. That's the chapter 7. So I put alpha r. So I get mr squared times alpha, where this mr squared is defined as a new quantity known as I. That I is moment of inertia. Okay. What is moment of inertia? Moment of inertia is the analog quantity to mass. Look, when we talk about Newton's second law, we said that the net force acting on any mass is equal to mass times acceleration. So for any mass that you are moving horizontally or vertically, you have more acceleration if the mass is less. So mass is the amount of inertia an object has. The more mass, the more inertia. But we just say inertia, right? It's a quantity, mass is a quantity of inertia because it lowers the acceleration. The more mass, more inertia, less acceleration. Okay. But what about that? In rotation, we just had this, that torque, the net torque acting on a body, on a rigid body, is I times alpha. Alpha is the angular acceleration. This is torque, which is the moment due to a force. So I makes sense that we call it moment of inertia. Is the analog to that. Is the quantity that reduces the angular acceleration of a rigid body. A rigid body is a body that is rotating without slipping, and that has certain mass and certain size, certain dimensions. Spheres, cylinders, discs, bars, those are all rigid bodies. And we can use them to calculate the moment of inertia. Now, if I were to show you how to calculate moments of inertia, that will take a whole class, because we define I in math. I is the integral of r squared dm. So as an exercise, in Calc 2, for example, we give you guys a bar with center on the origin, x-axis, y-axis, and we ask you to calculate the moment of inertia of that bar respect to when it's rotating around the y-axis. So this comes from an infinitesimal division on the bar. We need the density of the bar, which normally is just lambda m over L. the mass divided by the length. So we know that this is the x if you think about it. And then we put it here, and then this becomes x squared, and then we integrate it from 0 to L. And we get, it's very easy to do, but that's not the point of the course. So I'm just gonna give you the equations for the moment of inertia. But if you're interested and you know calculus, you can prove the moment of inertia of bars, disks, and more complicated to do the one for solid spheres. Okay? But then again, moment of inertia, which by the way has units of kilogram meter squared, is an analog quantity to mass. For translational motion, so for forces only, we use mass as the concept of inertia. Good. But for rotation, we talk about the net torque producing a rotation is equal to the moment of inertia times the angular acceleration. And you know the angular acceleration is in radians per second square. All right? And examples of that are what happens in pulleys. So now because of that, we cannot ignore the effect of a rope on a pulley. We can't, because the pulley can be modeled as a solid cylinder or as a solid disc, and it's being pulled, right? It's being pulled by a tension, so there is a torque, right? So those are some of the applications besides other ones, all right? So actually, let's show you here where you can find the slides before I move on. So that's what I just proved, all right? The rotational second law. If you think about it, that's what this is, right? The rotational second law, which can be written like that. The sum of the net torques acting on a body, on a rotating object, is equal to I alpha. All right? And in the textbook, they show you different ways to find the moment of inertia. So this is the algebraic definition of moment of inertia. So what's R? For example, if you have masses along a ring, the distance is R to the center, which is the axis of where the axis of rotation is going through, is passing through. So M1 R squared, M2 R2 squared. So if you do the infinite sum of all these contributions of mass, the moment of inertia for a ring is mr squared. Right? So for example, that's a very simple way to show you, to prove the moment of inertia for an extended object, in this case for a ring. For a disk, you can't do that because a disk has an area. So you have to use calculus for that. But like I said, in the textbook, they will just give you the formula. So here you have, and in the exam, you will be given this. And if you remember, when we did a lab on this, the students who did it, we use this, right? The solid sphere moment of inertia, okay? And this is important, again, because for these rigid objects or rigid bodies, when they are rotating respect to an axis of rotation, we can find their eyes. Now, keep in mind that, for example, for a sphere, for a cylinder, the axis of rotation is through the axis of symmetry. But for a bar, you have more than one. You can have one of the extremes, or you can have the middle, right? You can have a bar rotating around its center of mass. So depending on this, you have different values. Again, you can prove all of this using the equation I show you with the integral. And if you're taking calculus too, you do need to learn this, okay? At the end of the day, it's just to find your differential of mass. Once you know where it is and how to write the expression in terms of R, it works out, all right, depending on the symmetry, right? For bars, it's very easy. For cylinders like this, it's like a disc. And for hollow cylinders, it's like a ring. So these four are easy. These two are a bit more complicated, but at the end of the day, if you have to take calculus, you will end up learning that. It's like the volume thingy. Okay, so now that we introduce moment of inertia, we can extend some of the concept that we have done. So we're going to apply this in a little bit, but this is forces. What about energy and work? So if you have a sphere, right, center, which is moving to the right with some velocity v, radius r, on a surface where the sphere is rotating without slipping. That means it's doing pure rotation. That's what it means, okay? So you know that there is a W angular velocity equals to linear velocity over R, or V equals to WR. Now you know from chapter 7. Okay. So let's write down the kinetic energy of the sphere. So the kinetic energy of the sphere, so KE, is 1/2, this has mass M, mass of the sphere times V squared. But hey, we have that. So I want to put this there. So 1/2 M WR squared. Ah, but wait, that is 1/2 M R squared times W. And what is mr squared? Is a moment of inertia. So in general, the rotational kinetic energy is defined as 1/2 moment of inertia W squared times W squared. That is a general proof. If it was a sphere, the eye of a sphere is, or a solid sphere, is 2/5 of mr squared. So we need a factor here. The eye of a disk is 1/2 mr squared. So depending on the moment of inertia, it has its rotational kinetic energy. So that is a new equation. This is also measured in joules, by the way. So we can define the total kinetic energy, right? If the body is rotating, but is falling down or moving horizontally, it's still translating, it's still moving forward, but it's rotating as well, right? So it's doing this. So I can write my net kinetic energy. I have this. So the total KE will be translational plus rotational. There. Translation plus rotation. So that means that the kinetic energy that we were using in conservation of energy, well, for rigid bodies like spheres, right? We were ignoring that. We can't. That's why in the lab that you guys did, if you were to use just conservation of energy translational, your results will be very off, right? Because you're ignoring a whole factor there. All right. So now we have the concept of torque with angular acceleration, and we have this. Now, is there a relationship? Yes. Let's analyze. Let's do the analysis that you are going to need for a rigid body rotating down in an inclined plane. Most of you guys have seen this already because I showed you this in this actually whole whiteboard a week ago. Yeah. But now let's review it. And then we can do examples of this. So we can redo some of those examples that we did before, now introducing moment of inertia and torque. We can talk about pulleys. We can talk, so that is the idea of today. All right. And then we can talk about angular momentum. So let's analyze this. Oh, here. Angle theta, right? And then I'm going to give you a sphere. But now we cannot ignore that this sphere has some radius r. And let's say it starts at rest. And it's going to start rolling down the ramp with some acceleration. And it's eventually going to reach the ground with some angular velocity and, of course, some translational or linear velocity like that. So let's say that the ball started from certain height, r, h. And it has some mass m. And of course, we have gravity. So let's assume that there is no friction. So assuming no friction, the energy initial is equal to the energy final. It's at rest. So the only energy at the beginning is mgh, potential energy. At the bottom, that's the energy final. Translational and rotational, what I wrote over there. 1/2 mv final square plus 1/2 moment of inertia of the sphere. This is a solid sphere. Omega final square. All right. Now, the moment of inertia for the sphere is 2/5 of the mass times the radius square. Ah, okay. So let's substitute that here. So I will take all of this here. So MGH is equal to 1/2 MB final square plus 1/2, and then I write that here. That's the I and omega 5. Okay. So clearly we don't need a mass. Mass cancels. I have GH equals to B final squared divided by 2 plus 2 cancels. Okay. Always V equals to WR. So V squared is W squared R squared. So that W squared R squared is 1/5 B final squared. All right. So if I do the math here, I get that B final is square root of 10GH divided by 7. So if I were to ignore the rotation, it will be the square root of 2GH. Now is less than that, right? If I were to ignore the rotation gives you an extra kinetic energy factor, which changes your value of the final velocity, or in this case, the final speed. And as you remember, that is a more accurate value because the body is rotating and translating. All right. Now, we have ignored friction, right? What if we don't ignore friction? Can we do a similar analysis? Okay, so this is the energy analysis, okay? I will do a problem with numbers so you see how this works. We can redo the problem of the loop, by the way, using a sphere or a cylinder, right? So we'll do that, but let's analyze the sphere in a plane with rotation, with friction, all right? So let's see what happens with when there's friction. So I'll leave that in there for a bit. That's the energy. And let's see what happens if I do an analysis of the inclined plane. So I'm going to draw it here now. Same angle. Same sphere. With radius r. Okay. So why is a sphere rotating without slipping? We have to analyze what forces are acting on that object. Remember, we didn't talk about the acceleration, right? Can we find this acceleration? Well, let's see. If the sphere is rotating and is accelerating, it also has angular acceleration, right? Okay. So if I were to draw the forces acting here, from the center of mass is the center of the sphere, you have, well, first of all, you have this mg. And I don't think I have to explain this, but you already know this is mg sine of theta, and this is the component like that, mg cosine theta. Now, I said there is friction, right? So there is a mu kinetic on the plane. Okay. So if there is mu, there is friction. Now, friction always acts at the bottom, right, of the, even though it's in a sphere. So it's gonna act here. That's your friction. That's your Fk. See that? So just by using Newton's second law, mg sine of theta minus Fk equals to mass times acceleration. That's acceleration, and that's the mass of the sphere. Now, Fk is mu times normal. That's the normal. So I have this minus mu k mg cosine theta. So I don't need the mass. But I still have this expression and the sign for the acceleration, right? And this is like what we did in translation. But now that it's rotating, we can do an extra analysis. What is the net torque acting on the sphere? Right? If you think about it, hold on, here. The sphere, I'm going to draw it horizontally, okay? Has friction acting here and has this component. The torque acting on the net torque that is causing the acceleration, right, is the net torque due to friction, because this mg sine is acting on the point of rotation. The axis of rotation is an axis that goes perpendicularly like this, right? So this force is acting on the axis of rotation. So there is no torque due to this force. There is only torque due to Fk. But we know Fk. That's mu k mg cosine. And we know the distance to the axis. That's 90 degrees. Convenient, right? Radius. So mu k mg cosine theta, force times radius, Rf, that's torque, that's equal to what? Moment of inertia times alpha. That is how you apply forces, for example, on a wheel. Now, this is a sphere. So 2/5 of mr squared, and alpha, what's alpha in terms of acceleration? Alpha is linear acceleration divided by radius. That's chapter 7. So instead of alpha, I write A divided by R. And what happens is this. R cancels with one exponent, but this R cancels with this. So you have that mu k and the mass also. Mu k g cosine theta equals to 2/5 of the acceleration. And that's what you want, because this expression is here. So g sine theta minus this, which is that, 2/5 of the acceleration is equal to the acceleration. That goes to the other side. So you're going to get the acceleration equals to 5/7 g sine theta. If you ignore friction, it's just g sine theta. with friction, less acceleration. There you go. And that's more accurate than what we did before because we are considering rotation and torques and all that. Okay? So I just show you the equations that some of you used in the practical that we did, right? And this can be repeated with cylinders or discs. It will be different because the moment of inertia will be different. Okay? So we had the energy analysis. This is the forces sort of analysis. Okay? Where you have that the net torque acting on the sphere is equal to moment of inertia times alpha. Okay, so let's do some examples, all right, where you can see how this is used. And there are a few, so bear in mind there, okay? We start with a few simple ones. Yeah, for example, this. Okay. Let's see. Let's start with the rotational second law, all right? So in this one, they give you a large solid cylinder. Okay. All right. So let's draw it like this. So you have a cylinder. Like that. Yes, like that. Okay. You have a large cylinder, solid. So like this. And there is a tangential force acting on the cylinder. Now, the cylinder has radius 0.33 meters. And is rotating, right, due to a tangential force. So we draw a force like this, tangential, equals to 250 newtons. Apply on the edge like that. This gives you an angular acceleration of 0.94 radians per second squared. So that force produces that acceleration on this solid cylinder. The first question is, what is the moment of inertia of this wheel? This can be a wheel, or this can be like a cylinder can be used to model a wheel, right? You can actually, you can put it like this, like face on. So let's use this graph. That force is that force there. And it's accelerating, like this. So it's at that rate. All right. And that has the radius. So you have to use rotational second law. That net torque acting on the cylinder is moment of inertia times alpha. You have alpha, you want I, right? Because they're asking you calculate the moment of inertia I. So what is a net torque? It's just the torque due to that force. Force times distance. When they tell you that the force is tangential, you know that the tangent is perpendicular to the radius. So 250 times the radius, which is that radius, that's the torque. So you write 250 times the radius equals to I times alpha. Easy. And you find your moment of inertia. Right? So 250 times 0.33 divided by 0.94. 87.8. Your I is 87.8 kilogram meter square. It's a scalar quantity, by the way. The moment of inertia is a scalar quantity, like the mass. Questions about this? Nothing? Okay. So you found the I using rotational second law. Part B is asking you calculate the mass of the cylinder. And that's why I wrote this. The moment of inertia for a solid cylinder is 1/2 mr squared. You already know I, and you know the radius. So you can find the mass, right? I is 1/2 mr squared. Now I is that. That's 1/2 mass times 0.33 square. All right. What do you guys get for the mass?
$1,612.5.
Yeah, right. That's what I'm getting here. 1,612?
0.5.
That makes sense because that's like the wheel of a car. Yeah, that's like the wheel of a car. Or a truck. Okay. Let's review chapter 7. Because we have acceleration, right? So the last question, part C. They tell you that if the wheel had an initial angular velocity of 0 rads per second, calculate the angular velocity after 5 seconds. Calculate W final after 5 seconds. Okay, that's a chapter 7 question. What will you do? What will you do? Come on. I don't want to do it. You have to do it. Think somebody got it here. No?
Is it 4.7?
Yeah, because you multiply just 5 times that. Right?
Yeah.
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 That's just that. So that's kinematics, chapter 7, what we did. Make sure you review that, okay? You see how you can combine? That's a question that you can get in an exam. You have chapter 8, chapter 7 topics in that. And every topic is related because we talk about forces, torque, and kinematics. Everything in one question. Like, for example, look at this one. Let's talk about this now. Let's recall this. You have an inclined plane. You have a pulley. But now this pulley, it has certain... Okay, so let's do that. Now it's not just any pulley, it has certain mass and certain radius. Okay? So that's your pulley. And there is a string, and there is a box here. Now, the pulley has certain amount of rope, so the box is indeed accelerating downwards. The angle here is 37. The mass of this is 12 kilograms. They give you a lot of things here that I wouldn't, to be honest, but okay, 2 meters per second square. And they make it too easy because they don't put friction here, and I will put friction. But no friction, mu k 0. So, pare, calculate the tension on the rope. So that should be easy, guys. Do that. No friction, accelerating. So, right? Calculate the tension on the rope. Part B. Calculate the moment of inertia of the pulley. So let's see. The I of the pulley. And there's part C as well, so we'll do part C after, but all right. How will you do that? All right, guys. Anybody found attention?
$47.
How do you do it? What do you do?
I did mg sine 37 minus tension equals ma.
Yeah. Mm-hmm. Tension, mg sine. So that's m is 12, so 12 times 9.8 times sine of 37 minus tension equals to mass times acceleration, which is 2. Right? So you say 47, right? Let's double check. That should be about 47. Yeah, 47. You round it to 47. That's good. All right, that's chapter 4. Nothing new there. Part B. Calculate the moment of inertia of the pulley. Anybody did that? You can redraw the pulley here. You have a tension. You have the radius. Oh, they give you the radius. Wait. Oh, yeah. So the radius is 10 centimeters. So, okay. So you have the radius, tension, and it's obviously accelerating like that. So how do you find the eye of the pulley? Hmm? Remember that that is a linear slash tangential acceleration, right? So what equations do you need for this? What do you think?
I equals 1/2 mr squared.
No, because you don't know if it's a, they don't tell you what type of body it is. But, and you don't have the mass of the pulley. But you know that you have the force making the pulley rotate. So whenever you have the force and the acceleration, you write that the torque due to the tension is I alpha. And alpha, this alpha, remember from chapter 7, is linear acceleration over the radius of the trajectory, in this case, the radius of the pulley. So that's I times A over R. And what's torque? Torque is R times the force, RF. The angle is 90 degrees. So we don't have to worry about the sign. Sine of 90 is 1. So radius, which is 0.10, 0.1, radius times tension, which you found, 47, is equal to I acceleration over 0.10. And that's how you find your I.
Wait, I'm confused why we can't use the I equals 1/2 mr squared.
You don't have the mass of the pulley.
Oh, okay. Okay, thank you.
So if you don't have the mass, then you can't use that. Besides, as I said, you don't know what type of object it is, right? It can be a disk, it can be a cylinder, right? But you don't have the mass, so you have to use that. All right? So 4.7, 0.47 over 2, that's 0.20 something, right? 0.24 kilogram meter square. Here you are. So now you're finding a parameter of the pulley. And you know that the pulley is accelerating, right? 20 2 over, that's 20 radians per second square. All right? So another type of example that we did in the past, but now we're adding the whole idea of acceleration. Let's see, let's go back. Because we're using the eyes. So can we calculate eyes for objects? Well, let's do a problem like that. By the way, any questions about this?
No questions. I just have a quick question about the wording you said. You said to use this approach anytime we have force and the radius, or force and acceleration?
Whenever you have the tangential force and acceleration. Because even the radius sometimes cancels. So if you are given the force and the acceleration, you can find the moment of inertia. All right, because of this. Torque iron.
Okay, thank you.
Okay? But then how can, let's calculate I. Like we use this, rotational second law. But let's use the concept of I. And okay, like I said, to do the complex moment of inertia, you need calculus. But there is a simple calculation of I, which is for point objects, point masses. Like a situation like this. You have the X and Y axis. Like that. And you have four masses. Point masses. So one here, symmetric, so the same distance, like that. Symmetric here and here. So the distance here is of 4 meters. And this one of 6 meters. And the masses are 3 kilograms, 2 kilograms, 2 kilograms, and 4 kilograms or 5 kilograms? 4 kilograms. And they want you, and this is actually a whole like bar. Or like it's an object, and the main thing are these masses on the vertices like this. And this is the center, X, Y. You want to find the moment of inertia. respect to the x-axis. Okay, so this is the thing, right? Moment of inertia is a quantity that is only valid for objects that are rotating. That's what we talk about: spheres, cylinders, rotating bars. And in this one, you have four masses. And if they're going to rotate around the x-axis, they're going to do this. It's like they're going to be doing this, right? Like this. So how do I find I? I is going to be due to the contribution of the four masses. So you have a sum. So the I will be the sum of m r squared. And r is the distance to each mass to the axis of rotation. And the axis of rotation is the x-axis. So for the 2 kilogram mass, the r is free. For this one is also free. For this is free. And for this one is also free. Okay? Because that's the axis of rotation, like that. Okay? So my I will be 2 times free square plus 4 times free square plus 3 times free square plus 2 times free square. So you can factor free square out and they have 2 plus 4 plus 3 plus 2. 6, 9, 11 times 9, 99 kilogram meter square. That's the I respect to the x-axis. We label it like that. Okay. But what about the y-axis? What if the four masses were to do this? Right? If they were to do a rotation respect to the y-axis. How will you find I due to the y-axis? All right? What will you do? Now this is the axis of rotation.
Instead of 3 squared, would it be 2 squared?
Yeah. 2, 2, 2, and 2. Yeah. So it will be 3 times 2 squared plus 2 times 2 squared plus 4 times 2 squared plus 2 times 2 squared. So 2 squared, and the sum of the masses is here, 6, 9, 11. So that's 44 kilograms. You see, it depends on the axis of rotation. That's the respect to y, respect to x. So that's how you calculate I. At least you can do that. That's for point masses. All right. There's a more interesting one though. What if it's doing this? So like a wheel. What if it's rotating respect to the Z-axis. You think about it, that's the Z-axis, right? You have the X, or the Y, the X, and the Z. So what if it's doing this? What would be your R? If this is the axis, if this is a point of rotation. Hmm? Easy, guys. You find the distance from each mass to the origin. That's it. Now we are. Let's call it R1, R2, R2. Oh, they're all gonna be the same. How will you find the R? Three, two, how do you find R?
Pythagorean theorem.
Exactly. Square root of 4 plus 9, 13. So they all are the same. And I'll let you guys think about that. That's a question in the web assignment. So I did A and B. So for C, we'll have to use 2 times R squared plus 4 times R squared, which is just square root of 13. So it's not bad. Now, what can you be add? What can you add in this question, though? You have the I. If where can I put this? You have the Ix, Iy, and even Iz. What if they give you the angular acceleration? So let's write here. If every rotation has an angular acceleration of 1.50 rads per second squared. So if each of those has that acceleration, find the torque produced. So niche here. Let's find the torque. So how will you find the torque? If you have alpha for this I, what's the value? How do you find the torque if you have an acceleration, guys? What's the equation?
I times alpha.
I times alpha. So I alpha. So we just use 99 times 1.5. That's for this situation. For this, torque will be 44 times 1.50. What's the value of each? This should be 66 Newton meter.
The top one's 148.5.
148.5
Yes.
Newton meter. All right. Not bad, right? You see? You calculate you can calculate torque. After the break of 10 minutes, I'm gonna do energy problems, guys, and a few more of this. And at the end, we'll talk a little bit about angular momentum. All right. And that's it. So 10 minutes, guys, and then we continue.
Okay.
Nah, nah, that exam is gonna be all multiple choice. No, no, just the formula sheet. Yeah.
Okay.
In terms of calculators, were we allowed graphing
Yeah.
calculators?
Yeah, you allow any calculator. Any calculator is allowed. Equation sheets I'm gonna provide. Scantrons, 30 questions, multiple choice. So the questions won't be too difficult. It's 2 hours, so you're gonna have a lot of immediate type of questions, right? Where you have to calculate this, calculate that, right? The exams are more challenging than the final exam. That's in any general physics class. Okay.
And I know you had encouraged us to do our own equation sheets. Are those going to be allowed, or is it just going to be the ones you give out?
Nah, for the final, we have to provide you one. Normally, the department makes a final, but for summer classes, we do the exams.
Okay.
But at least the equation sheet has to be given by us. Okay.
Yes, thank
All right. And this could be a question, like a type of question like this can be in a final. It's very direct. A conservation of energy question, right? You have sphere, a solid sphere. With that radius, rotating without slipping until it reaches the end of the ramp, 6-meter ramp. Find the angular velocity at the bottom. Very easy. Remember, there is also be final. Tangential, right? Linear velocity. So it starts at rest. Find W final. So since there is no friction, the initial energy, mechanical energy initial, is equal to mechanical energy final. Because the sphere is at rest, the initial energy is just potential. Okay, so we need the height of this, right? What's the height of this? Then you do the angle. You have the hypotenuse, 6. How do you find height? Hmm? How will you find the height?
6 times sine 37.
Yeah. 6 sine 37. 18/5, that's 3.6 meters. All right. So mass of the sphere, gravity times height, equals to the energy at the bottom, which is rotational plus translational kinetic energy, 1/2 mass B final square plus 1/2 of I omega final square, or W final square. So M 9.8, 3.6 1/2 mass B final square plus is a solid sphere. 1/2 parentheses 2/5 of mr square. That's the moment of inertia of the sphere times W final square. So that's why you don't give it the mass, because the mass cancels. So 9.8 parentheses 3.6 equals to B final squared divided by 2 plus 2 cancels. And I show you this in before, right? W final square times R square is B final square. So that's B final square divided by 5. So yeah, we can just calculate that. This is 35.28. And that is 7 B final square divided by 10. So B final is 10 times that, the square root of 35.28 times 10 divided by 7. 7.10 meters per second. But wait, that's the linear. I want the angular. All right, guys. How do I find W final if I have B final? What do you do? That's chapter 7, so you should know that by now. Hmm? B final over R. 7.10 divided by 0.2. That's 35.05. Yep. So 35.1 radians per second. And it is.
Wait, I think it's
Energy problem. A typical energy problem. Like I said, I can change this to a cylinder. You will just have to change the I. Okay. In fact, let's do another one here. Any questions before we change? It's like what we did before, right? I mean, you've done this in chapter 7, in chapter 6, conservation of energy. It's just that now you're adding the rotational. It's the same idea. All right. All right. And if you did a lab on this, then you know. The same with the torque lab, right? The torque lab helps a lot for the whole idea of torque, and then the energy lab for this. What situation can you be given with energy? You can be given this. You have this axis of rotation, and you have a pulley. This pulley is wait, what? Okay, so yeah, it's just a pulley rotating like that. But it's because it has a rope all around the pulley. All right? And at the end, it has a bucket or a mass. This mass is of 3 kilograms and it's going all the way down. And it's gonna fall towards the ground. How much it falls? 4 meters from rest. So it's like you let it go. They want you to find the angular speed of this. And you assume this to be what, though? You assume this to be a solid cylinder. It's a solid cylinder. And you want to find once it reaches the ground. So once the bucket is here, it has to be final, right? But the cord, the rope, is going to be also here. Right? It's going to go down. So that's going to make this gain some W final. So you want to find the final angular velocity of the pulley if the mass of the pulley, well, the radius first, is of 0.6 meters and the mass is of 5 kg. You got the mass and the radius of the pulley. Hint. Use conservation of energy. You could use forces, but no, use conservation of energy. So how would you think about this? Right, you have a pulley there, which is because a rope, and then you let this mass go, it reaches the ground, and then that's why the pulley gains some energy due to the angular velocity. What energy does the mass gain, guys, from here to here?
Kinetic.
Kinetic, right? And can you find BF? It starts from here to here. We've done those problems before, guys. Forget about this for now. How do you find the final speed of the mass? Hmm? You have the height. So what do? You
Is
can
it
use,
initial squared plus
huh?
2a? Initial squared plus 2a? Plus times the height? Or no?
Yeah, like potential energy equals to kinetic energy for this situation. What's the potential energy of 3 kilograms at this height? Hmm?
MGH.
MGH. MGH. What's the kinetic energy? 1/2 mv final square. It doesn't matter. So what's BF? 80 square root of 80. 9. About 9 meters per second, right? Is that right?
Yeah.
Yep. So that's the energy. That's BF. In fact, I'm doing an extra step just to review because are we going to use that? Maybe. This energy comes from where? From here, but also comes from here, right? It's a whole system. We're not in friction, by the way. So all the energy from the pulley, as it's rotating, goes to the falling mass. If this is a solid cylinder and it's just rotating, what's the energy on the pulley, guys? How do you find the energy of the pulley? Hmm? What's the equation for the rotational energy?
1/2 mr squared.
Yeah. So the rotational kinetic energy is 1/2 I W squared. That's why they give you the mass and the radius because it's a solid cylinder. Now you can find I. W is what you want to find. This energy is this energy here. Due to kinetic, but hey, I didn't need to find this. The potential is equal to kinetic is equal to rotational. The potential 3 times 9.8 times 4 is equal to kinetic, but it's also equal to 1/2 I is, okay, the I for a solid cylinder is 1/2 mr squared. That's the I, okay? So 1/2 mass of the cylinder, the pulley, radius square multiplied by W final square. And you solve for W final. You solve for W final. That's it. 3 times 4. Oh, caramba. 3 times 4 times 9.8. That's 117.6 joules. That's all that. So 0.36 times 5 divided by 4. 0.45 W final square. And then we divide by 0.45 and we find W final is the square root of 117.6 over 0.45. So that should be 16.2 radians per second. There you are. another energy application there. Is that the only analysis we can do? Let's suppose they were asking you for the tension on the rope. So you see, there are different questions you can be asked. Here they ask you for the angular velocity of the pulley. What if they ask you for the angular acceleration or the tension on the rope? That you need forces analysis. Let's do it. Okay, let's do that. Any questions about this? It's just conservation of energy. The energy on the bucket came from the energy of the rotating pulley. So rotational equals to translational. That's basically it. Okay. We even calculated BF at the end. You can, it's an interesting situation, but let's find the tension on the rope. So we can leave the same. All right. Now let's ask other questions in there. You have this mass, you have that, it's accelerating downwards. Let's say that you were being asked, find the tension on the rope. Okay. So what are the forces acting here as it's falling towards the ground?
mg.
Yeah. What else? Mg, what else is acting there? What's this? What's this?
Tension.
Tension. So it's falling. When we did the adult machine, right? It's sort of like that. What will be Newton's second law for the mass? Hmm? There. Mg minus tension equals to Ma. But you, that's free, right? So we have this. Free times 9.8 minus tension equals to free A 29.4 minus T equals to free A. Okay, we have two variables. The next equation comes from the pulley. What type of force is the tension on the pulley, guys? What type of force it is?
Tangential?
Tangential. Very good. So a tangential force produces what? A what?
Centripetal?
A torque. A torque, guys. So this tension acting tangential to the pulley is making the pulley rotate because of the torque. So on the pulley, what's the torque due to the tension? This is 90 degrees. It's the radius. Tension times radius, RF, sine of 90 is 1, equals to I alpha. And I know I, because it's a solid cylinder. So now I have the mass. Now I can find I. Let's see this. Tension, radius, 0.6, 1/2, mass, radius squared. And what's alpha in terms of A? Instead of alpha, what do I write? Hmm?
A over radius.
A over radius. A, look. 0.6, 0.6, 0.6, 0.6. Cancels. So tension equals to 2.5 acceleration. How nice. Look at this. Now I can put that in here. See, I have a relationship there from the tension with the acceleration. So that's what I get. This comes here. So 29.4 minus, instead of T, 2.5 acceleration equals to free acceleration. The algebra, 29.4. This is 5.5a. So acceleration is about what? Like 5? Yeah, 5.3 meters per second square. How nice. I found the acceleration. Then I can find the tension. Right? I found that here. The tension on the rope is 2.5 times 5.3. $13.4 newtons. You see, everything that we've done in the course is kind of in here, right? Newton's laws, we did energy, torque, angular acceleration. Well, we talked about energy right in the previous, but there you are. So the part B can be find the acceleration or find the angular acceleration. Like, what's the angular acceleration of the pulley? If you have A, you just do A divided by R, and you find the angular acceleration. So, any questions? You sure? All right. So, there's a couple more problems I want to do, but let's finish this chapter by introducing the last parameter. Remember, we talk about forces, torque, right? Energy, rotational energy. And in chapter 6, we talk about linear momentum, right? Well, what happens when objects rotate? You have angular momentum. And this is important, guys, because when Kepler discovered that the orbits of the planets around the sun were ellipses, there was a very important law, the second law, that planets sweep, and I show you this in the animation, right? planets sweep equal areas in equal time. This is true, but he wasn't able to mathematically prove that, right? And the reason that's true is because of what you are seeing in front of you. And that was discovered by Newton, right? When he discovered the gravitational force, he realized that that's the force responsible for the objects orbiting the planets orbiting the sun. Furthermore, he discovered, well, thanks to the force, we have our definition of energy, potential, kinetic, and like I show you, and it makes sense, right? There's no friction in space. Energy of a planet orbiting the sun is conserved because the gravitational force in that trajectory, right, the work done by the gravitational force is zero. So there is no net work, energy is conserved. But it's an isolated system. In an isolated system, energy can be conserved if the gravitational force is the only force acting, okay? But also momentum, but not any momentum, angular momentum. And they don't give you the definition per se in there, although they tell you that the net torque acting on a mass is equal to the change on angular momentum per unit time. Basically, the rate of change of angular momentum. So, Kepler's second law basically states that the change in angular momentum for any planet orbiting the sun is zero. Using that, you basically prove that planets travel equal areas in equal times because they travel more distance in the perihelion than in the aphelion. Just so you know, perihelion is the shortest distance from us to the sun, from the Earth to the sun, and the aphelion is the largest distance from the Earth to the sun. Okay? So the perihelion basically is when the Earth is around February, January, February, and the aphelion is around July, right? The difference in astronomically speaking is negligible, right? So that's why we can assume the orbit of the Earth to be like a circle, but still, we know that there is about 9 to 10 million kilometers difference between the aphelion and the perihelion. Anyway, so L, capital L, is the variable for angular momentum. Is a letter that we use. And you have there, right? You have a mass orbiting or in a circular motion, and you have the net force tangential to the mass. Why do we draw it like that? Because in that case, there is a net force acting. If there is a net force acting, then there is a torque acting, F times R. And that torque is equal to the change in angular momentum per time. In the case of planets orbiting the sun, there is no F net. There is only gravitational force. And that force is centripetal, right? So it's perpendicular to the tangential trajectory. So basically, there is no torque produced, right? Because it's like this. Therefore, the angular momentum is conserved. Right? Now, let's show you that equation there because I don't like the way they do the proof in there. And for that, I'm going to have to use a bit of calculus, so just keep in mind how we're going to show you the relationship between angular momentum and moment of inertia. And then we can show you a few examples, like where do you see that in real life, besides planets and, you know? So the mathematical definition of angular momentum, L. So angular momentum L is a vector, by the way, defined as R cross P. So basically, if you have a mass rotating with some velocity, some distance r. Mass p, as you remember, is your linear momentum. R is the level, is the distance. This is called distance. So for an object in circular motion, this is a mathematical definition. That's the cross product. If the velocity and the distance are perpendicular, in this case, angular momentum, the magnitude is just RP, which will be RMV. So, you know what are the consequences of this? If L is MVR, think about planets. It's an ellipse, right? That's the sun here. That's the Earth on the perihelion, the Earth on the aphelion. So this is R for this point. This is R for that point. I'm exaggerating it. So the larger, the mass is constant. This is constant. We know that. Angular momentum is constant in the whole orbit. So if you increase the distance, what happens with the velocity? It decreases. So what Kepler realized, kind of, right, is that at this point, V, let's call it V2, and here, V1, he realized that V1 is greater than V2. Why? Because this distance is closer to the sun than that. And that's what we know now in rocket science. The closer you are to a star, you can use that to gain kinetic energy and do what you know as a slingshot. You can use basically conservation of potential energy and kinetic. But that's because as you get closer to the star, in this case to the sun, your velocity increases. All right? So that's why a planet here might cover this area, but for this planet, it will be as this. Same area, but the planet travels more distance here than here. All right? That was the consequence of that. Using this simplification. Okay. Now, let's talk about the definition that you have in there. The net torque acting on a mass is the rate of change of angular momentum. But guys, you have to write it like this. Because at the end of the day, torque is the first derivative of angular momentum with respect of time. So what you can do is torque dt is your dl. But what's torque? Torque is I alpha dt. That's dl. But alpha is dw over dt. So it cancels. I integrate on both sides, and I get that my angular momentum is I is a constant, dw is just w. There you are. So angular momentum is a multiplication of moment of inertia times angular velocity. Let's do the analogy. Let's check this. Let's check this and this. Just like we did with energy. So my linear momentum was defined as a vector P equals to mv. My angular momentum is I W. So what did I say before? Mass is a measurement of inertia, moment of inertia. Linear momentum, angular momentum, linear velocity, angular velocity. Makes sense. It's the same idea. Your angular momentum is a product of the moment of inertia times the angular momentum. So if the angular momentum is constant, right, then if you increase or to increase the angular velocity, you have to decrease the moment of inertia. And moment of inertias, for example, for in general, moment of inertia is mr squared. So if you decrease the distance to the axis of rotation, you decrease the moment of inertia. Ergo, you increase the angular velocity. Where do you see this? You see this in planets, formation of planets and stars, but you also see this in here. So when a person pulls his or her arms closer to his axis of rotation, you are reducing the value of R. Therefore, you are reducing the moment of inertia. Therefore, you are increasing the angular speed or the angular velocity. That's why the person is spinning at a faster rate when his arms are pulled towards his body. And then when he or she stretches his body, his moment of inertia increases, increases. So his angular velocity decreases because you are increasing the R here. We see that in planetary formation, right? The conservation of angular momentum, we can see it as planets or stars are formed. We have the nebular theory of how the sun was formed. Basically, a very large cloud started to fragment, and then it flattened like a disk. And then as it was shrinking, it was gaining velocity by the conservation of angular momentum. Okay? And eventually, that's how planets are formed. And they end up rotating around the hosting star. It's more complex than that. There are more processes. But there is a conservation of energy because where is that energy coming from? Gravitational potential energy, as the cloud is shrinking, is being converted into kinetic energy, right? And heat. And that heat and pressure and temperature, we're going to talk about next week, that ignites the star. All right? So that is basically how we know solar systems, star systems are formed. All right? So the conservation of angular momentum in two different situations there. Okay? So questions, by the way, about this? So it makes sense, right? We talk about in this chapter 8 and a bit on 7, we did the analogy of what we did in linear to what we have in rotation. Right? And it's very important because every object in the universe rotates. So, well, most of them, right? So we need that. We need to understand that to be able to answer questions regarding those. Okay? So there's an example here. Look at this. We did collisions before, so let's do it again. You have put this down. You have a bullet. She's shot towards a door. The door is like this. There's a support, a hinge in there. They give you the mass of the door, the speed of the bullet, the mass of the bullet, and the bullet is gonna embed itself 20 centimeters from this side, so this is 20. The door is 1 meter long. And they ask you a few questions, right? For example, before the bullet hit the door, does it have angular momentum respect to this axis of rotation? And then they ask you to find the angular speed after the collision. So the bullet is gonna hit, and then they're gonna go all the way till here, right? So just like previous examples in chapter 6, angular momentum is conserved. So there is angular momentum before the collision and after the collision. The door is not moving, it's just there. The only thing that's moving is the bullet. So right at the moment that the bullet strikes the door, the bullet has angular momentum respect to the hinge. And that angular momentum is conserved when the bullet and the hinge and the door, they both move with some angular velocity that we can find. The only thing that is not conserved is mechanical energy. Because if you think about it, it's a perfect inelastic collision. In a perfect inelastic collision, there is no energy conserved. And that's part of the questions here. Calculate the energy after and before, right? To show that they don't conserve. All right, so let's do it. Okay, you have the question there. I'm gonna draw it here. And let's see how you will do a question like that. So you have, again, a hinge. And you have the door. Of a bullet. Which is gonna strike like that. And the speed of the bullet, 1,000 meters per second, with a mass of 0.00530 kilograms. The door is of 14 kilograms. All right. So obviously, before the collision, after the collision will be like this. Right, this is before, after. So now it's not linear. So angular momentum initial is equal to angular momentum final. That's why they ask you if there is angular momentum of the bullet, because the angular momentum of the door is zero. It's not moving. This is when you have to wonder, right? What equation for angular momentum I should use? Because there are two equations. You have angular momentum R cross P or angular momentum IW. For after the collision, that makes sense because they want W I is the I, and they tell you that the door can be assumed to be the door can be assumed to be like a bar, like a rod. Okay, so it's like a bar respect to the axis. So the moment of inertia is 1/3 ml squared. That's the length of the bar. Okay, that will be after IW. But what about before the collision? The initial angular momentum is the angular momentum of the bullet right before it strikes the bar respect to the hinge. So I will use that. Why? Because you have linear velocity. You have this. So the initial angular momentum for the bullet will be mass of the bullet times the speed of the bullet times the distance to the axis of rotation, which is 0.80 in meters. MVR. For a point mass, it's better to use that. Okay? So yeah, the bullet has angular momentum respect to the axis of rotation. So the equation will be mass of the bullet times 1,000 times 0.80. Oh yeah, the units for angular momentum are kilogram meter square per second. Okay? All right. So that angular momentum is equal to the final angular momentum, which is the momentum of the bar and the bullet. So this IW 1/3 mass. What's the mass of the door? The door plus bullet, 14 plus that, so 14.00530. So 1/3, 14.00530 ml. That's just one square times W final. Yeah. So now I can just use the math, right? Let's find this. Let's find that. So 0.0053 times 1,000 times 0.8. That's 4.24. All of this. Let's see that. That's 14.005 divided by 3. That's 4.67. W final square. So W final is that divided by that square root. About 0.95 radians per second. So that's how you find your final W. Okay? That's how you use conservation of angular momentum. And now we can use that to prove that the energy is not conserved. The energy before, the energy after. This will be just rotational energy because it's just rotating. All right? So 1/2 I omega square. And you can do that. You can compare. The kinetic energy of the bullet is way, way higher than the kinetic energy of the bar and the bullet, like 1/2 I omega square. It will be way less than that. It's a perfect inelastic collision, so it's not gonna be conserved. All right. Questions about that, guys? Okay, so that's one. Let's see this. I'm gonna do another one, and then I'm gonna do a review problem. All right. Not that. Still another one. Another application for this is it's angular, is merry-go-rounds. I'm trying to look for an example here. I'll see if I have it. Okay, let's see. Okay, we did that. Let's do this one. IW. Yeah, let's do that one. So let's do the merry-go-round example. The typical example is if you have merry-go-round like this, it's gonna be like a disc, right? Well. And you have a person outside traveling at certain velocity. I'm gonna give it 6 meters per second, constant. And it's going to, from the edge, it's gonna jump to the merry-go-round. Let's give some values here. So let's say the disk. This is a merry-go-round, this is a disk with mass. Okay. Let's give it 500 kilograms and radius 12 meters. Okay? So the radius of this is 12 meters. And it's rotating before the person jumps. The merry-go-round is rotating at 20 reps per second. That's W of the merry-go-round. After the person jumps, the person is gonna land 8 meters. All right, so after that, you're gonna have again the same merry-go-round. And the person on here. At 8 meters. Traveling at different W though. That's what you are being asked. The mass of the person, let's make it 50 kilograms. All right. So it's a nice situation, right? You have a boy or a person who is traveling at this speed, and when he or she is on the edge, it's gonna jump. It's gonna land like that. And it's gonna start, the W is gonna change. So this is a classic example of angular momentum, conservation of angular momentum as well. The angular momentum initial is equal to the angular momentum final. So the merry-go-round is rotating. It's a disk without mass, without radius, without W. So it has an angular momentum, IW. So the L for the disk is IW. But as the boy is about to jump, it also has angular momentum, right? This times this. And when he's on the edge, the distance to the axis of rotation is 12. So you have angular momentum. They both have angular, just like the bullet, right? It also has, that's the initial, the before. The after will be both of them together, the boy and the merry-go-round, traveling at the same W. All right. So you have to be careful for this because there are a few things you have to think or to remember. So for the before, right? The merry-go-round has a mass of that, radius of that, is a disk. So the I for the merry-go-round is 1/2 500 times 12 squared, I times W, that's the initial of the merry-go-round, plus what is the angular momentum of this person? If you have the mass, I told you right now, you have the linear velocity and the mass, mv times r. So plus mass times velocity times r. That's the whole angular momentum before the person jumped. Let's calculate that. So to make it smaller. So 500 times 144 times 20 divided by 2, 720,000. Plus this is 50 times 6 times 12. All right. 56. Okay, so 3,600. So everything is 7,023,600. That's the initial angular momentum. The final will be the moment of the IW for this, and the angular momentum of the person. But, okay, for the merry-go-round will be 1/2 times 500 times 12 square times W final plus, okay. So now I need the angular momentum of the person 8 meters from the axis of rotation. So how can I write that using W? When the object, or you can use the equation as well for him. His angular momentum can also be IW. What's the I for that person? mR squared. And W is just W final. So here, it will be the mass of the person. So the moment of inertia of a person is mass times the distance to the axis squared. So mass times 8 squared times W final. And that is how you solve this. So let's see. 723,600 equals to, okay, let's calculate that. So we have 500 times 144 divided by 2, 36,000 W final. Plus 64 times 50, 3,200 W final. So I just have to do the algebra. 36,000 plus 3,200 is 39,200 W final equals to this. And I just divide. 73,600 divided by 39,200. 18.4. All right, yeah, it reduces a bit. I get W final 18.4 rads per second. That's a more in-depth problem of conservation of angular momentum. Now, this topic again is not going to be on the exam, but it's going to be on the final, so just beware. All right. Take a look at some of these examples in Cengage, but the main thing is the definition of L, your angular momentum. All right. Any questions? Okay. I want to show you, we have time.